Bonjour, my name is Sebastien POULIOT. I'm from Quebec City, Canada. Some of you may see in my accent that I'm French speaking. Like about 8 million people in Quebec. Have been working on Mono. I started contributing back in Mono in 2002, in the summer, and then I started working at Novell in 2004 on Mono itself. Went back to the Novell layoff, the start of Xamarin, and then the acquisition by Microsoft. Since the Xamarin days, I've been working on Xamarin.iOS. It's been a fun ride. So that's my little short story. I'm a bit curious about the people here in the room. Can just a show of hands, people who have done some mobile development work, okay? And people who have submitted something to the App Store. Okay, fewer people. You may have noticed that I did not raise my hand. I have not submitted something myself to the App Store. I have done some app development as part of the job, but I'm mostly a tool writer. So my job and what I do is to write tools, not write applications. So I guess that a lot of people here will be a lot better than me to write such applications. So my talk will be focusing about the tools and how we can, well, a lot of challenge to create and transform .NET code into native code, and how the tools try to raise to the opportunity that we have to create native .NET applications. Okay, so quick, let's see how we build .NET on Windows. That should not be a shock for anyone. It's fairly standard. So we have source file, we compile them. Now everyone use Roslyn, the CSC compiler, and we get assemblies. Those assemblies have intermediate language, the IL, and some metadata. Now, the execution part is interesting because the assemblies are PE files, so the portable executable format, and that means that Windows can load them, and when Windows sees such a file, it will also load the .NET execution engine, and then that will allow it to continue to load all assemblies that are required and to jet your application. So works, well, it was made to work together. A lot of things can be shared on Windows, like the class libraries and everything that you can put into the global assembly cache. So we can share a lot of things. The way it works, when the assemblies are loaded, the execution engine starts the JITs, and then everything gets JITs into memory. So it's very nice because it gives you very small files. The IL is very compact compared to native code. The native code that is generated, you never see it on disk. It's only in memory. And everything, a lot of things, not everything, but a lot of things can come either from the BCL or something in the GAC. So you can have a very small executable size for a very complex application. Okay, so now if we move outside of Windows, there's a lot of other operating systems, and .NET works on most of them. The first thing is to build applications or any code on .NET, and this is basically the same everywhere. And that's probably the slide I like the most, the easiest one so far. Now, the problems start when you want to execute those applications, because the PE format is native on Windows, which also means that it's not native anywhere else. In particular, for macOS and iOS, we use a format called Macho, and Macho, well, is not compatible with PE. So we require a native launcher, something that will include, well, at least the launcher, but that will start or include the execution engine on that platform. Mono does that, so the Mono executable itself is a Macho executable on the Mac, and it includes the JIT and other tooling, the runtime, and all that stuff inside that executable. And that's why if you type mono with the name of your assembly, you can execute that assembly. Macho does not fill the bill for everyone. So it does the job for me because I'm lucky and I do only command line interface tools. But if you want to do any UI, then it won't work because this is not what macOS will load for a UI application. To do so, you need to have what we call an application bundle. Anything that ends up with a .app extension on a Mac is normally an application bundle. And if you want to do any UI stuff, you will need to interrupt and call some ObjectiveC API. So how can we allow this on .NET? Well, it's simple. We need a tool. So we're starting to talk about those tools. We need a tool that will package and that will follow that convention. It's really a simple convention. The .app is a directory, and it describes a hierarchy of directories, and where you have to put the right resources in the right place. If you mess it up, it won't work. So we can include inside of that the launcher, the execution engine, which must be Macho executable. We can get inside that your assembly, so your code that you have done, any dependencies that you have that can be native dependencies. At the end, it must be code sign and all that stuff. And at the end, you get your Mac application bundle. And this will work. That will provide an icon. It will work from the desktop. You double click on it, and it starts, and it looks like just any other Mac application. So the next step, you want to call and you want to use ObjectiveC API, the stuff that Apple gives you on the OS. Now, to do this, we need to create bindings. We need to create something that you can use from C# to use those API. So there's tools to do this. What we ask people is to create a definition, which is some C# code that describes the API that you want to end with. We compile this, and then from that compiled temporary assembly, we generate code for the final bindings, and then we recompile a second time that code to give you a binding assembly. And this is the file that you will include with your application to access those API. There's two parts for bindings. There's one that comes to mind. You want to do something, so you want to call an API. So that's the easiest. We are generating code that are p-invokes to low-level ObjectiveC runtime function, which mostly work by sending message to objects. We do a lot of type conversion. So as .NET developers, we like to work with system strings. We don't like much to work with C strings, and NS strings are not much better. There are all of kinds of callbacks. We like to use delegates, pretty easy. Not so much on ObjectiveC. They are all reference count. So we have all that logic there to get this to work, so it's invisible for most of the developers. What we don't think as much is that, and the way ObjectiveC works and how Apple does their API, it's very common, is that ObjectiveC needs to be able to call back inside your application. So if you do a UI table view, you will need to have a UI table view delegate, and this is called directly from UIKit. UIKit is made in ObjectiveC, so it means that it needs to call back into C# code. ObjectiveC itself cannot do that. It does not know anything about C#.NET. So what we have to do, we have to generate what we call trampolines. So we generate a bit of code, ObjectiveC code, that would get called by Apple and UIKit, and then this call will convert back all arguments. Again, if it's a string, well, it receives an NS string from the operating system, is going to convert that to a system string, and then we will call the .NET API. All of this gets generated, compiled, using not .NET, since it's Objective-C. So the native toolchain will compile it, and we need to include this with your application to work. Okay, so up to now, we were able to do something on the Mac, show a UI on the Mac. So basically, we should have everything we need to work on iOS. It's the same app format that they use, the app bundle. They have the same requirement for Objective-C, Objective-C API. We need to call it. We need to be able to receive calls from it. And if you run the iOS simulator on the Mac, it works. So what are we missing? Well, we're missing a lot, actually. The thing is, there are a lot of restrictions on iOS. A lot of them are in the execution and how you have to do stuff. But there are two that affects the tooling a lot. First one, we cannot do code sharing. So anything that looks like the GAC is not possible anymore. We cannot share the mono runtime between applications. So every application must be self-contained. The next one is that we're not allowed to JIT. So everything we talked so far, mono, .NET, it's all been about JITting code. We get the IL, we JIT it. In memory, we execute that memory. Well, iOS does not allow you to write in memory and then execute that memory. Okay, so let's talk about, or let's solve that first problem. Having a shared application is not always a good thing. People have found out with the .NET framework over the years that if you update from 1 to 1.1, well, you can have them side by side, 2.0 side by side. Next comes some service pack, and then whoops, your application crash. Something has changed. And you cannot have side by side different versions of the same .NET 2.0 runtime. So either you can fix your application or find an updated application, or you run into the problem that you have to select which one you want. And if it was updated for security reasons, well, you're probably better with the later one. There are many solutions for that. Along the last 20 years, we came up with the empty bundle for Mono, which was basically bring everything into a single file and then execute that single file. That will bring the execution engine, the JIT, and all that stuff. For the Mac, we did that differently, mostly because we have an application bundle. It's already a directory. So we can put everything that we need inside that directory. So that includes native dependencies, that includes debugging symbols. It also includes the BCL, and that can be quite large. So we can fix that problem, but it also introduces new problems. So the next one, a little bit more complex. We cannot JIT. So we cannot just-in-time compile code at runtime. So if we cannot do this at runtime, what can we do? Well, we can compile before, at build time, whereas, well, all older non-managed language normally do their builds. The process is very simple. You give assemblies to the AUT compiler. It generates native code. Biggest difference, it does not generate that into memory. It will generate it to disk. And then you can bring that into the application bundle. That also brings, well, without really solving the original issue, it brings a few more. What the AUT people don't tell you, because that kind of technology exists for many managed language, is that in most cases, the AUT compiler still needs the JIT compiler to be present. Two reasons. One, there are stuff that are really hard to AUT. If you have a list of T, well, every type at runtime could be inserted into that list, so you will need to generate code for all those variations, even if at runtime they may not be needed. well, there are ways to share code and all that stuff, but it gets very complicated for value types, all structs, native types and stuff like that. Also, one of the reasons that they don't, well, that they include the JIT is that we need it for system reflection init. So if you want to have a real .NET complete with all the features, you still need the JIT even if you use AOT. So in most cases, AOT is used for better performance, reduce startup time and stuff like that, and not just like what we want, uh, not being able to JIT on the device itself. And like I said, well, if you are bundling the managed code and the native code inside the application still gets larger. So the way to solve it is what we call full AOT. So what it means that, well, if AOT, everything is hard, well, we'll have to do it the hard way. So yes, we're going to AOT everything. We're going to try to share everything that we can, and we can make it work. Mono is the only execution engine that has a full AOT compiler. You will have other AOT compiler. People may remember in the early .NET engine. After that, you have CrossGen, you have .NET Native. There's a new CrossGen in the work, or maybe a release recently. None of them are doing a full AOT job. So it's an exclusive in Mono because we had that kind of issue on iOS and some other platforms. Gaming platforms in general, like Xbox and PlayStation and all that stuff, they also require full AOT. So all that hard work does give us a few pros. We don't need to JIT at execution time, which means that the application can pass the Apple guidelines for the submission. It also means that we don't have to ship IL inside the assemblies. And that's a nice side effect. Well, we save a little bit of space, but the nicest one for most people is that it's much harder to decompile native code than IL. I'm guessing that a lot of people had the chance in the past to decompile IL, either with some tool that decompile or IL spy and tools like that. It's very easy to find out what's the code look like, even decompile backs to C# and all that stuff. Well, if you don't have the IL, you cannot do this. It also gives us new opportunities because the application cannot be extended. It's not possible anymore to create code with system reflection in it. So if you have a type, now we know if there are subclasses of that type or if there's none. So we can seal the type, even if it was not in your source code, because we know it's not going to be extended. We can finalize methods. The dot final, it's not really much used in C#, but it's possible. We can devirtualize methods because we know that they won't be called using virtually, and all that stuff. Well, and we also get some problems. If we really AOT everything, well, we still get bigger application. And we lose the ability to run with the API or Allo API that use system reflection in it. That includes stuff sometimes that we don't really think about, stuff like dynamic system link expression. They're all using kind of dynamic code and generation under the hood. In some cases, like system link expression, we already we put an interpreter there, which gives us most use case correctly. So maybe people never notice, but by default, it will not work. Okay, so we talked few slides, I've been pointing out that we're getting bigger, and bigger. So at some point, we need to do something so that we will not file your phone for a single application. Those are multi-application devices, so it'd be nice to have more than one .NET application running on them. So we do another tool, which is a managed linker, which does about the same thing as a native linker will do with static libraries. It looks if code is being used, and if it's not used, it does not put it into the final executable. We do the same thing. We get all your code, all the BCL and everything, and we look if that code is reachable. That's done using static analysis, so it has some limits, which is why by default we only do what we call link SDK. So we read everything, we only modify the code that we own. So the BCL, the bindings like in Xamarin.iOS DLL, and stuff like that. It's possible to do it for user code, but then you're responsible to make it linker friendly. It means that you have to int the linker if you are doing operation like reflection. It's not possible for the linker to guess that you will have type, the get type of A dot get methods of B dot invoke null. That will call any type, well, any method B on the type A, but those A and B, they can come from user input. So such code will mean we cannot link. But it's easy for application and for developers. You can put the ints to the linker and tell it what it should keep, in addition to what the static analysis itself has found. What it gave us fewer assemblies, because some assemblies we realized that, well, they were referenced, but we don't use it at all. And they get smaller. An example, if you do an hello world on Xamarin.iOS, you're going to see that the only assemblies we have after linking is ms_lib system, which is only 5K, very small things there, Xamarin.iOS, and your executable. And with full AUT, it gets about 6 megabytes. If you don't link and you do the same thing, you're looking above 200 megabytes. So there's a lot of code that your application is not using. Okay, so we solved quite a few problems, even the size one. But there are still things that we were not able to do until recently. So in the last year, we introduced an IL interpreter. We made a choice years back that if we could not JIT, well, we could AUT. We could do it before. There was another option that we did not take at the time, which was we could interpret the IL. I started to develop, well, the first software I wrote was on a VIC-20. Not sure if people know what it was. It was the computer made by Commodore before the Commodore 64. It has a whole 5K of memory, and it was running BASIC and interpreted BASIC. So interpreting should be possible. Not much I can do now with 5K. I'm not sure how it kept me busy when I was a kid, but it was a nice computer. So if we interpret IL, what do we get? Well, we get things back like system reflection limit. So it's now possible to generate code, even on device, generate assemblies that we can save. You can download new code. You can download update code that you already have. We can remove stuff like or old interpreter for system link expressions, because we now have an IL interpreter at a lower level, so we get much better compatibility. Now, there are some drawbacks to using the interpreter. Mostly the reason we did not do it before. It's slower to interpret than to run native code. But the funny thing is that it's not that much slower in many cases, because your applications often are using, well, you're calling API from the platform or from other native code. So those are already compiled, so they are fast. So sometimes you're just inside the loop that dispatch events. And being interpreted is not a big difference. I was very surprised the first time I saw the IL interpreter work. I was testing this with Xamarin Forms, And I was pretty sure that the watchdog will kill my application because it will take too long to start up. And it did not. In fact, I had to double check because I was sure that I missed something. And that I was using an AOT version cache somewhere or something. I mean, it was not as fast because after that, you kind of use a watch and you make sure that you're not making any mistake. But it's fast enough, and that's interpreting everything. But since we were expecting performance issue, we had other ideas in mind. Uh, we knew that MS-Corlib is very special, very low-level code. We did not want to interpret that. We also know that Xamarin.iOS itself is largely, well, it's binding, so does not buy you very much to interpret those. So we decided to build a mixed mode. So it's possible to say, well, my application has some, let's say a game. I have some OR logic that must be very fast because it affects the rendering, it affects how the video are played, the sound, and all that stuff. But there's a lot of AI code that I like to, well, I like to create new levels, create new personage, or anything, and bring that to the application later. And all that code could be using the interpreter. So you can mix and match what is AOT and what is interpreted into your application. Uh, Doing so, of course, if you use the interpreter, there are some global optimization and, that we cannot apply anymore. Everything that I said that we can assume that we know everything about the application is not true anymore. That type that we were sure no one was subclassing, we can't be sure anymore that it's never going to be subclass. The IL removal cannot work in that case. Well, if you AOT the assembly, we can still remove it. But if you ship something else for interpretation, we cannot remove the IL because it's the code that's going to be written. Not always a bad thing because IL is more compact form than native code, so it can also reduce your application size. But those are cons to think about if you want to use this. Okay, so with all of this, we kind of have solved the puzzle of how we can run .NET on iOS. And we can create a tool, an orchestration tool, a meta packaging tool that will do all this. In Xamarin.iOS, we call that mtouch. That's what the IDE is calling. You may have already seen this in build logs and stuff like that. You mainly only have to give it your main executable. It has the entry point. And from that executable, we can resolve all the assemblies that are being used. They are all referenced. We give all of that to the linker. The linker will tell us what we really need. So a lot of those assemblies will be removed. The tool continues and then call the AOT compiler, creates all that native code, brings that up into the application bundle, adds the native launcher, the execution engine, the registrar code, which is the code that allows Objective-C to call back to you. And then optionally, we get the IL interpreter added. Every other resource that you added to the application, bitmaps, sounds, video, custom documents, and all that stuff, we sign the application, and you get an application bundle that you can submit to Apple. And in many cases, the size don't really differ that much from an Objective-C or Swift application because, or 6 megabyte for Hello World has a lot of like the execution engine and all that stuff there. But once you start to add logic, it grows very slowly. Same thing with our other language, it's just that our initial it is a little bigger than other. Okay, quickly. So we have it on iOS. What happened for TVOS? Anyone here has been using TVOS? Oh, nice, nice, nice. It's one of my favorite platforms because there's only one architecture, ARM64. It has an Ethernet plug. It's not on Wi-Fi, works much better in the business environment, in the office and stuff like that. It's very fast compared to the other platform. I really like it. Uh, so it's pretty much the same as the restriction for iOS. Uh, when Apple started this, they wanted to remove a lot of things, stuff that they allowed on iOS, and they, well, after thinking a few years on it, they decided, well, maybe we should not expose those things. Uh, that did cause a few problems, but we could work around those. There were other ways to do what we wanted. The big change was that they required bitcode to submit. But in that case, they do allow what they call in the bitcode inline assembly. And it turns out that what the AUT compiler does is assembly. So we just tell the bitcode, well, we say bitcode, open quotes, the AUT output, close quotes, and that's what we send to Apple. Just good. It's bitcode. Okay, so what about watchOS? Anyone here is doing some watchOS development? Ah, you have a nice job. Great. WatchOS is, well, the watch itself, I love my watch. The development on the watch is not as fun as the iOS or TVOS. It's much more complex. There's a lot of things I think are missing. Even Apple does not ship a unit test framework for the watch. So it makes it hard for us to automate some of the tests that we're doing and all that stuff. Uh, Otherwise, it's mostly like the same restriction as iOS and tvOS, except that Apple removed more stuff. The things that people noticed the first is that they remove sockets, cause some problems for debugging and stuff like that. It's kind of useful to have a mechanism to exchange data. They also remove a lot of low-level API, and those kind of hurt us because it means that we cannot run the garbage collector anymore. So we come up with what we call a cooperative mode. So normally the garbage collector can stop, we call that stop the world. It can stop every thread in your program at some point and say, well, I'm now collecting memory. That requires some API to control the thread that are not existing or not allowed for us to use on watchOS. So in that case, the cooperative mode, what it does, it defines save points at some place in the runtime where the GC can stop everything. And we cannot do that when a thread, or at least on a thread, that is only a native thread. So it's a different mode. It has advantages because sometimes, like in game development, you don't know exactly when the GC is going to run, and if it runs at the wrong time, well, you're going to get some frame drop and drop frame and all that stuff. So people like predictability, and it's more predictive when you have a cooperative GC because it can only happen in some places and not in others. The other change is that it also requires bitcode, but in this time, they did not allow us to just ship the inline assembly. So that means that the mono AUT compiler cannot be used to create those images. But we have a Clang LLVM-based backend, and we can use that backend exclusively in that case to generate what we call the intermediate representation, IR, which is kind of similar to IL, just a little bit less general. And this is what we need to use for watchOS. The drawback, since we cannot use mono, is that Clang does not do everything that .NET does. Exception filters, not sure if a lot of people use exception filters in their code. It existed for a long time in .NET, but not in C#. That's more recent. LLVM does not support them, so we need to kind of hack around it. So the behavior is not identical, so it's not perfect there. But otherwise, we can have this .NET work on watchOS with those few small limitations. So what is the future of .NET on iOS? Well, the first big thing, people may have heard about Swift. Started about now 5 years ago. Apple came up with a new language. Objective-C was quite old, so it was really a subset of what C# could do. So they decided to take a really long jump ahead, and they created something that was more like a functional language than Objective-C could be. So it's more like F#. And they said, well, next version, Swift 2 is going to be ABI stable. And the next year they say, no, Swift 3 will be ABI stable. And the next year they say, well, Swift 4, and after that, Swift 4.2. And at some point, it was becoming a running joke. And they say, well, Swift 5 is going to have it. So come last spring, Swift 5 is out. Apple said, yeah, we have ABI stability, but you don't. So what it means that they could ship Swift libraries on the OS, and you could use them, but you could not create your own libraries or framework and redistribute them as binaries. That only came in September of this year with Swift 5.1 and what they call the module format stability. We did not wait for Apple to release something ABI stable to start to work on this. It's kind of a huge project because, like I said, it's a superset of C#. So there's a lot of new features there that they don't really map to C#. But if you want to use the API that expose them, well, we need to find a way to make this available to developers. So it's been in work for a few years now, and I had to change my slide, I don't know how many times. But it was open source this week. It's called BTFS, for Binding Tool for Swift. It's on GitHub. It's not fully complete. There are a few things that are still in development, but it's welcome to contribution. So if you had Swift code or Swift libraries that you have seen that you found interesting in the last few years, this is the tool that will allow you to bind them and include that inside your application. It's a bit like Objective-C. We have an Objective-Sharpie tool that did some of that work. The nice thing about Swift is that you won't have to create binding definitions, because Swift has a lot more metadata available than Objective-C has. So we can create the type and name the API automatically because the data is there, when we were lacking that for Objective-C. So it's a lot more complicated, but hopefully it's going to be much less complicated for the people that consume the tools. So we're going to keep that complication on our side, unless you want to join in the fun and the open source version. Pretty much it for Swift itself. The other big thing is .NET 5. You may have heard this week or in the last few months about the next big version of .NET. So we're going to share across all runtimes. We're going to share a lot more code. There's going to be two major execution environment, Mono and the .NET Core one. In our case, at least, not for the Mac, but for iOS and this sister and brothers operating system, only Mono can work because of that full AUT I was talking about. But it means that everything else is going to be shared. So we will be switching to the core FX, CLR, base class library code. So it means that when a new feature comes out, like span, what was the other one, the direct interface methods and stuff like that, you're going to have this release across all the SDK at the same time. It's not that .NET Core is going to release something and then at some point this is going to be happening on the other SDK. We're all going to be using the same source. There's not going to be some adaptation and stuff like that, unless something is not possible on the platform. There are always platform-specific issues that we need to deal with. And that's about it. If people have questions, I'd be happy to answer them. Yes.
I've actually got a couple. Thanks, Sebastian. You mentioned the what was the term for the garbage collector on WatchOS?
The cooperative mode.
Cooperative. So I've seen the checkbox for concurrent garbage collector for
Yep.
iOS and Android. Is that similar?
No. The quick answer is no. SGen, which is the GC that we now use on Mono, and the only GC we support on iOS and others, has a lot of smaller modes. In that case, it allows you to do more stuff in parallel. It's called parallel, concurrent, so you may have guessed a little bit. That was not a big thing in the earlier device because they were single core, but now that we have multiple core, it becomes something that is interesting. So you can share the load across the cores. It was in prototype for a couple of years because it's very hard to say in a lab or in a testing environment that the GC is fine. That's not how it works. GCs are a very complicated beast, and when you think it works, you call it experimental, and then you let people try it for quite a while before it becomes available. It's a bit like what happened with cooperative mode. It's been something that the people in the Mono team has been thinking for quite a while. WatchOS kind of forced us to get this out faster than usual. But like I said, it has some nice things about it. It's more predictive and all that stuff. So it may be used in other platforms in the future.
Cool. Yeah, I mean, I know I've been using it in my production apps for probably years now. It's always been fine. But even though it had the experimental tag on it, I figured, why not roll the dice, right?
Yeah, it was removed at some point. I don't recall exactly which version, but
Right.
at some point the folks from the Mono team told us, well, you don't find bugs, we don't get bugs from anyone else. I guess it's good enough.
Nice. And second question is about the Swift bindings. Because Xamarin.iOS is all built off of Objective-C, right? Or bindings to Objective-C. I guess the question is, would we move to using Swift, and like, would that benefit the team since, like you said, like the APIs are more defined, so you don't have to do as much work?
The operating system is still in Swift. The major no, not in Swift, in Objective-C. Most of the frameworks are still in Objective-C, or they export in Objective-C. Sometimes it's not clear, but what the export is. So we don't expect that to change very, very soon. What Apple is doing, they are doing their own bindings in Swift. So what you see as a UI table view with a bit different API is a little layer of Swift on top of Objective-C. And we have no plan to bind this because it will break all the source code that exists. And if they have a good idea, a nicer API, well, what we will do, and actually we did this in a couple of places, well, we do the same thing in C#. It's much easier than trying to bind Swift and to get to the same result. This year there was, I don't remember the name, but there was a framework that was only in Swift, released in iOS 13. We know that other applications from Apple, like the stock application notes, stuff, are written in Swift, and they are shared between macOS and iOS. So we know that internally, people at Apple are using Swift a lot more. Makes sense for them. I mean, it's a much nicer language than Objective-C was.
Yeah, it's interesting. I didn't realize Swift was just built on top of Objective-C like that. So
it's not.
My question doesn't even make any sense.
Swift itself is not, but it has a lot of language feature to ease its interoperability with Objective-C. But the OS itself and all the frameworks are mostly in Objective-C. We don't know what the future holds. Still, stuff like Swift UI are showing things, and now we know that at least on iOS, we know that deep down it's still Objective-C, but what they expose is Swift. So at some point they could decide that they switch into a different implementation that will be Swift only. That's possible. They expose stuff on the watch in Swift UI that is not available on other platforms. We know it's on the watch, but we are not allowed to use those API. But if you use Swift UI, you are allowed. So.
Fascinating. Thanks.
Other questions? Okay, well, thank you, everyone. It's been a pleasure being invited to the update conference. I hope you enjoyed the presentation. Thank you.